Good afternoon and welcome to this Chemistry World webinar. Today we're looking at trends in modern hit discovery and how your ultra-large screens can benefit from machine learning. I'm Ben Valsler, Chemistry World's digital editor. My role here is to guide you through the platform that we're using and introduce our speaker, and then I will be the voice of your questions. And speaking of which, let's go straight to how you can ask questions in the GoToWebinar platform that we're using. Now, GoToWebinar, depending on whether you're using a phone or the web browser, will have a panel that probably is down the right-hand side of your screen. And usually towards the bottom of that, there is a box where you can ask questions. So type in any question that you have at any point throughout the presentation, and we'll have about 15 minutes after the presentation to go through as many of your questions as we can. Any questions you have about the content will be great. Hopefully I can answer a few of your questions about webinars in general before we get started though. Two really important things to note. Firstly, we don't share slides from our presentations, and instead we make a copy of the entire thing recorded available for you. Now we do this because we think that the slides on their own are not as valuable as the slides with the presentation that's been given. So it's important for us that you hear what's being said as well as seeing what's happening in the slides. So we send you a link to the recorded version rather than sharing any slides, and that will be in your inbox in a couple of days' time. And for all of you who attended live, all of you who are still arriving now, I can see, you will get in the same email a certificate of attendance just to show that you've joined us today. So keep an eye out in your inbox in a couple of days' time for that certificate and a link to the recording. And do keep your questions coming in throughout the presentation. Don't wait until the end in case we do run out of time. At any point, if anything occurs to you, ask that question straight away. The advantage of using a webinar platform like this rather than just live streaming a video or even just putting a video out onto YouTube is that you can engage, you can get involved, and you can ask your questions. So do keep them coming in. We will also have a poll where we find out a little bit more about you as an audience, and that's coming up in just a minute or so. So what are we looking at today? You've seen the title on screen there. You can also see a picture of our speaker. I'll tell you more about him in just a minute. But we know that traditional structure-based virtual screening has been very successful so far in finding diverse hits that can be used to advance projects. But there is still significant room for improvement. Now, ultra-large, on-demand, synthesisable libraries from vendors have enabled a roughly 100 times expansion of the purchasable compound space, which now numbers billions of compounds, and DNA-encoded libraries can be even larger. Now, in this webinar, we'll be exploring how machine learning approaches can be used to more effectively screen these enormously large chemical spaces. So we're going to look at how the approaches can make it easy and cost effective to find novel hits through virtual and DNA encoded library screens of billion-plus compounds. We will look at how machine learning can be trained to experimental DNA encoded libraries and therefore reduce false negative rates. And we'll look at the benefits of ultra-large screens and how they can replace the more traditional technology. Now, our speaker today is Matt Rupasky. He's Senior Vice President of the Life Sciences Products and leader of Schrodinger's Scientific and Technical Support Groups. He received a PhD from Yale University in chemistry, and he's published extensively in the area of structure-based virtual screening and provided leadership in the development of software products in the areas of docking, pharmacophore modeling, conformation generation, and QSAR modeling. One of his key roles has been as product manager of the industry-leading commercial docking application Glide, where he's been since 2006. It's a ligand docking program for predicting protein ligand binding modes and ranking ligands via high-throughput virtual screening, very much what we're talking about today. And unlike other programs, Glide approximates a complete systematic search of the conformational, orientational, and positional space of the docked ligand. We're going to share a couple of links in the chat with you so you can learn a bit more about Glide, and you can pick those links up now and then read more later. Very interesting reading, and I've been told that one of them is the journal it's published in is one of the single most cited papers that journal has ever published. So clearly it's important, and it's good that we understand these techniques and methods in order to push science forward. Now, I will hand over to Matt in just a second, but first, as I said, let's learn a little bit more about you. So we're going to launch our poll now, and we're going to ask you this question. So the impact of machine learning methods on your research is it periodic and limited? So it occasionally has a small impact. Does it occasionally have a significant impact? Is it frequently used, but it doesn't really have much of an impact? Or is it essentially an everyday, really important function for you? Is it common and significant? And we're going to give you a short while to get your votes in. I can see a lot more people have come in since I started. So a little reminder, we'll send you a link to the recorded version. If you find that your connection breaks down, don't worry, you'll be able to catch up with anything that you missed. And we'll also send you a certificate to say thank you for coming. So keep an eye out in your inbox for that, which will arrive in the next couple of days. Now I can see the votes coming in. I can already see that we do have a clear winner, but it's starting to even out. So once again, the poll on screen at the moment, the impact of machine learning methods on my research, is it periodic and limited, periodic but significant, common and limited, or common and significant? How would you say machine learning methods are affecting your own research? And just about half of you, I think, have now voted. So I think that's probably enough. We'll close it down now and we'll see where we are with this. You can see how you fit in with the rest of today's audience by having a look at these results. As you can see, it's quite an even spread, actually. So just slightly over the rest, 32% periodic and limited, but clearly 27%, over a quarter of you here today, have common and significant impacts from machine learning approaches on your research. So you can see how you sit in with everyone else, and hopefully for all of you, regardless of where you sit in that poll, there'll be key things that you can take away from today's presentation with Matt. So once again, I'll hand over to Matt Rupasky, who's Senior Vice President of Life Sciences Products and leader of Schrodinger's Scientific and Technical Support Groups. We'll get him up on screen. He will share his presentation and we should hear his voice very soon. So Matt, thank you very much for joining us. Very much appreciated. We can see your presentation already. I think you are on screen too. And I will hand over to you for now and come back for some Q&A after your presentation. Thanks for joining us.
Fantastic. Thank you very much for having me. It's my pleasure to be here talking with you all today about some of the recent research at Schrodinger in hit identification of billion compound libraries facilitated by machine learning. So two projects that I'll discuss today. The first explores the use of machine learning to enable cost-effective structure-based screening of billion compound libraries, such as the enamine real and WuXi lab network libraries. And in the second example, I'll show how through collaboration with WuXi, we're using machine learning to reduce the number of false negatives and identify compounds with better properties, coming as suggested as hits from DNA encoded screens of billions of compounds. So traditionally, purchasable library space has included up to around 10 million purchasable compounds. These are the pulled off the shelf libraries, and it covers only a tiny fraction of the accessible chemical space that's typically seen in hit identification. So the advent, though, of these on-demand combinatorially synthesized libraries has drastically expanded the purchasable compound space into the billions and tens of billions of compounds. Now, the approaches from vendors like Enamine and WuXi, where you're using large libraries of building blocks combined with very reliable reactions in a single step reaction kind of cascade in order to be able to generate a large number of products that can be created very reliably with organic methods. So they've basically created these purchasable compound library spaces, and Enamine has publicly suggested they have 80% ability to actually synthesize any of the compounds that are in the Enamine real library, which is largely borne out by what we've heard from talking with other collaborators. And so this really opens up a huge range of chemical space for virtual screening, both in terms of the types and number of chemotypes that are available, as well as the decorations, the number of decorations to each of those chemotypes. Now, another fact is that these libraries are large today, and they're continuing to grow significantly. You can see here, Enamine real space is already around 30 billion compounds. So these are massive spaces continuing to grow. Now, even larger than these purchasable on-demand libraries are the theoretical libraries available for DNA encoded library screening. Now, these are also built on a combinatorial approach They can start in the hundreds of millions and theoretically can be as large as 1 trillion compounds, though for reasons we'll discuss later, most screens today are nowhere near that. They're in the single-digit billions of compounds today. So we have access to these large purchasable compound libraries, but should we really use them? I mean, we've been finding hits with the more traditional 10 million compound libraries. And one of the things that we've been very heavily influenced by here at Schrödinger was work that's been done by the Choquette lab, where they, a couple of years ago, brute force docked 100 million compounds from zinc into the D4 and AMPC targets. And then they experimentally assayed around 400 compounds from different scoring tranches coming from the docking. And there were a number of several interesting discoveries that were made in that work that really suggest strongly we should be screening billion compound libraries preferentially and identifying ways to make this more cost effective. So first, they found a relationship between docking scores and hit rates for the experimentally assayed compounds, which is shown in the plot here. At low docking scores, so most favorable docking, the hit rate was consistently in the 20%, 26% range. For this target for D4 here, which is similar to the hit rates observed, I'll show this later, across a broad range of targets for GLIDE. Now with worsening docking score, hit rates also continued to worsen until they become nearly zero at a score here of around -45. Now, there are obviously false positives, false negatives. Docking scoring functions are far from perfect. But it shows that this relationship exists, even when looking at very large numbers of compounds in the 100 million range, strongly suggests that the intrinsic level of false positives and false negatives in docking doesn't impact the signal coming from the true positives. And this suggests that throwing a very broad net to find the best scoring compounds possible is a strategy likely to identify hits. And on top of that, the hits that were found were advantageous over hits from the more traditional 10 million compound screen. So 3 of these compounds, this guy, and this individual here, were 10-fold more potent than any of the D4 receptor screening hits that were available or people were aware of at that time. And this includes studies that were really biased towards the dopaminergic chemotypes that dominate the D4 target. There was another compound, unfortunately I didn't add it here to the slide, apologies for that, that was found. It was the best compound found. It was 180 picomolar inhibitor, which came straight out of the virtual screen. Now, no compound that's topologically similar to that compound was found in the smaller in-stock libraries, and it was really the expanded chemical space of the on-demand library, in this case zinc for this work, that expanded both the number of chemotypes and the number of decorations found per chemotype that enabled that ligand to be found. So this was very influential in our thinking and really got us wanting to use GLIDE to screen these very large compound libraries. And the work before I showed was from Doc. GLIDE performance is quite good. And so we believe it can be used in these large scale libraries and show performance similar to better. So virtual screening, I'm going to focus on GLIDE today for the rest of the talk, and wanted to set expectations on the performance to expect. And so in pose prediction, you're taking a ligand and you're docking it into a protein structure without a ligand. And then what we can do is we can compare to known ligand crystal structures and recognize the pose prediction accuracy. And across the Aztec set of structures, GLIDE finds a sub 2 angstrom pose in a little over 80% of the cases. And this gives an average RMSD of 1.14 angstroms, which is very, very good. So it means basically take home message in roughly 80% of targets, you're going to find a pose that is going to be suitable for use moving forward for a structure-based design type of project. Secondly, looking at enrichment. So enrichment in this context is the separation of compounds that are likely hit ligands, so they're going to have activity in a binding assay, from compounds that are unlikely to bind to that conformation of the protein binding site. And across a wide range of targets, this is DUD results here from a few years ago. Glide has shown consistently good performance across a broad range of targets in enriching the top-ranked compounds in hits. And as shown here, on average, Glide is recovering about a quarter of known hits within the first 1% of screened compounds, which is very good relative to other docking program performance. So we want to apply Glide to screen these large-scale billion compound libraries, but screening even 100 million is expensive. Screening billions becomes prohibitively expensive. So if we assume cloud costs for compute, and this all just uses CPUs, so no GPUs here, of 1 second per ligand, we assume the docking program performs 1 second per ligand, and we're assuming a cost of 6 cents per CPU hour, which is pretty inexpensive here. Just performing an experiment, docking experiment on 1 billion compounds is going to cost around $16,000 in just pure compute costs. And then I mentioned earlier, these libraries are expanding rapidly. If we wanted to be able to screen somewhere near the larger enamine set, you're looking at compute costs for a method that only takes 1 second per ligand in order to process of around a little over $300,000. Okay, so clearly brute force docking is an approach that you can use. You just have to accept that it's going to be expensive in terms of compute costs. And eventually, at the 50 billion compound range, we're likely to hit in a few years, you're going to be spending $800,000 simply on the compute costs. So we really wanted to pursue, particularly after brute force docking the 100 million with Glide ourselves, whether there's a smarter way to do this. And any approach is going to have to scale on a per compound basis much better than brute force, at least in order of magnitude. And you want to evaluate as many compounds as possible with the most accurate scoring sampling approach you have, which in this case would be Glide for us, and be able to sample chemical space with a far less expensive method. Now, deep learning methods theoretically can learn any function, and we found that they adequately reproduce Glide docking scores. We're primarily concerned about the areas in the far lower left-hand side of the plots here. We actually don't care that much about reproduction here, where you don't have very good docking scores. Those compounds are being ignored anyway. So we wanted to ask the question, can we use the fact that we can decently reproduce docking scores, but not super accurately? With deep learning methods, can we use that in order to help facilitate sampling of chemical space? One of the things that we became very interested in through previous work that had been done with free energy perturbation calculations was active learning. And it's active learning here is a method of iterative supervised learning. It's commonly used when you have a very large set of data that you need to make predictions on, but scoring them is expensive. Sometimes it has to be a human who does the scoring. Sometimes it's expensive algorithms. In our case, it's going to be the latter, and expensive here is about 10 seconds per ligand. Some of the most common applications, people use it for speech recognition, information extraction, classification, and filtering. And one of the things is that it can handle very large numbers of molecules in training, which is fantastic. And we already have methods that can perform the key steps necessary for an active learning process, where you start with a large data set that doesn't have any property predictions on it. You then decide which compounds to send to the learner. The learner in this case would be Glide, and you're learning the docking scores. It labels the data set, some subset of the data set, with docking scores. You then train an ML model against those docking scores. And then you use that model in order to pick new compounds to continue through this iterative process. So you're basically sampling chemical space with a machine learning approach to find what it believes is going to be most successful, and then using Glide, in this case, as the source of truth to actually label each of the compounds and help guide the machine learning method towards the most optimal solutions. And we already have Glide in this case, and we're using our AutoQSAR DeepChem-based method in order to be able to perform the machine learning training. AutoQSAR DeepChem, it implements an automated approach to neural networks by implementing graph convolutional neural networks that are available in the DeepChem package of Pande. The GCNN model is kind of like a neural fingerprint that operates on a molecular graph. And in addition to the GCNN networks, the AutoQSAR DeepChem also constructs random forest models based on Morgan fingerprints coming from the RDKit 32 cheminformatics package. All right, so this is all available in the suite. We combined these approaches to build the active learning glide workflow, which is overviewed here. And basically, you have billions of compounds library. You select a subset. This is all done automatically via workflow of around, tens of thousands, 50,000 is the default here. You run glide SP docking to generate poses and scores. We train an ML model. Now, this is typically run on a GPU for speed reasons against those 50,000. Then we score the entire billion or billions compounds library and rank them by the ML prediction. We then take some subset, a new subset of 50,000 compounds, pull those out, send it to the learner of Glide, and we can keep on then training an ML model, this time against 100,000, so 50,000 from the first subset, 50,000 from the second subset. And in this way, you can keep on iterating until you decide whether your ML prediction is good enough, at which point you can move on, or you continue looping. Okay, so in this way, we're using the ML method in order to be able to sample the compounds, to make decisions about the compounds to be included into this training set for explicit glide docking, where then we can use the correlation between the ML model and the glide docking in order to say, yep, we should continue to find compounds that are found by this model, or we need to iterate the model. All right, now one of the key factors of active learning is how you decide on the compounds to send to the learner, so this subset selection. And where we found three methods, we've developed three methods here from ideas, other ideas in the literature. Nothing here I would argue is really novel, but there's a random selection method that was the initial default. We changed over to an uncertainty-based method earlier this year, and then very recently we've gotten results on a wide range of targets that suggest strongly a diversity-based selection method is the most favorable, where we're looking at the chemical diversity and maximize chemical diversity. Now, the uncertainty here is because AutoQSAR, that's accessible because AutoQSAR DeepChem generates a collection, an ensemble of different models from combinations of different ML algorithms, combination of different featurization schemes. And because we're using a consensus prediction method, we're able to get uncertainty out of that, and that spread and variance in the predictions coming from the consensus method give us this uncertainty prediction. All right, so very important how you decide to select the compounds to send to the learner, in this case, Glide. Now, to give everybody a much more concrete view of how this process works, I'm going to walk through an example from a full workflow. So starting from scratch, we've got, say, a billion compound library, and we select 50,000 compounds from the diversity selection algorithm. We'll run glide SP docking on the top 50,000. Then 75% are selected for training, 25% are used for a holdout set of the glide data that's used in training the ML model. We'll train an ML model, and then we'll score. And again, this ML model is actually a consensus of multiple models. We'll then score the entire data set, the billion compounds, rank order them. And then from the top 10% of the scored compounds, we'll select 50,000 from those using diversity selection. And that 50,000 then is added to the original 50,000 compounds that were selected. We run glide SP on our new 50,000, and then we train an ML model against 75% of the 100,000 compounds here, with 25,000 used as a holdout set. We then train a new ML model. Again, it's going to be a consensus, multiple models under the hood. Rank or score the entire billion compound data set, and then from the top 10% of those ranked compounds, select another 50,000. Okay, now we've got 150,000 compounds. Again, run the glide docking on the new 50,000. We now have 150,000 scored with the expensive learner, glide SP here. Again, we train a model with the same 75-25% split. And then we'll typically stop at this point. And then we'll use that ML model, again, a consensus score of multiple models under the hood, and generate ML ranked predictions. We then typically will take these ML ranked predictions and run a glide SP docking on the top 1 to 2%. It says 10% here, but for the larger libraries, it's really 1 to 2% to obtain the true docking scores. So in this way, by docking only 150,000 plus whatever you decide to dock explicitly of the top ranked ML predictions at the end of the day, let's say 1%, you can examine these very large chemical spaces in a very finite number of expensive docking runs. And the ML predictions we're making ML predictions in this case against 3 billion compounds, let's say. And so you can do this in a very cost-effective manner because those ML predictions are very, very fast. All right, in order to, we've run validation against brute force docking. We've also used this method in a number of virtual screens from our drug discovery and applications group, and it's been very successful. I'm going to talk here about some work to validate where we looked at the Choiquet data from their Nature paper that I showed earlier. And what we wanted to look and see how well Glide performed with an active learning context against just if you did the brute force docking. And so we took the original zinc-based data sets, and this the zinc data set here was developed from on-demand synthesisable library. So it's very similar to the enamine and Wuxi libraries. And so we used the same compounds they used, about 100 million compounds. We brute force docked them with Glide SP. And then we ran the same experiment, but using active learning Glide. And we used 2 rounds of active learning in that case with 100,000 ligands for each step. So comparing brute force docking, where you examine 100 million compounds, around 100 million compounds explicitly, versus an experiment where we examine 200,000 compounds with docking in the training step, and then screened a tranche, a much smaller subset, 1 to 10%, to examine performance. And we wanted to ask, how well does the model recover the best scoring compounds that Glide found in that 100 million brute force with active learning? How well do we maintain the diversity of the chemistry that was identified by the best scoring compounds? Is the ML only examining and taking us to certain regions of chemical space, or is it broadly able to recognize a wide variety of the chemistry involved that are found as hits? And finally, how well does active learning recover the experimentally verified hits? All right, so what we found was very, very strong recovery of the top scoring compounds from the brute force docking with Glide SP in the active learning approach. So the results here for 2 targets, D4 and AMPC, and we took the top 10,000 ligands from the Glide SP brute force, and we looked to recover those. How early do we recover those in the ranked list from an active learning Glide process, where we had 2 rounds of training with 100,000 ligands each round. This actually used the random, the diverse would be better for the learner selection. And then we scored with Glide explicitly the top 2% or 3% or 4% coming from the ML approach, which then generated the final rankings. So the final rankings are based off of the explicit Glide docking of the top 2% by the ML model, the final ML model, 3% by the final ML model, etc. All right, and so we're concerned here with the red bar here, which shows the active learning approach. And you can see for D4, excellent recovery of the top 10,000 scores or compounds that Glide brute force would have found in the active learning approach, well over 90%. For AMPC, we're finding around high 50s if you screen on the rescore only the top 2%, which in this case would be 2 million compounds. If you're willing to screen 5%, you're recovering more like 75% of the compounds. So we're saving, I'll talk a little bit about this later, but somewhere around 95% of the compute costs relative to brute force approaches with an active learning screening approaches and we're recovering overwhelming majorities of the compounds that would have been found had you brute force screened these libraries. So that's a very positive result for active learning glide. But what about the chemical diversity? Are we giving up the ability to find the broad range of chemical diversity, which is one of the advantages, intrinsic advantages of a docking approach over, say, a more ligand-based, QSAR-based approach? And take home here is that yes, the active learning approach is able to recover the overwhelming majority of the chemotypes that were found by the brute force docking. So here we're comparing the top 10,000 ligands, the diversity. We clustered these top 10,000 ligands by SP glide score using ECFP4 fingerprints with a Bettina clustering algorithm that's in RDKit, and we use a Tanimoto threshold of 0.5 in order to do this. And so there were 3,622 total chemotypes from that analysis coming out of the brute force. If we just look at the active learning ML ranked compounds, the top 10,000 of those, with no glide rescoring at all, we find 631 of those of the 3,622 chemotypes are recovered. So we're recovering about 17% if you just take the straight up active learning predictions and using those without any kind of glide rescoring at the end. Okay, and that suggests what we saw earlier when you saw the reproduction of glide score by the machine learning approach. There's clearly a lot of signal there, but it's not perfect. And so that's what you're seeing here. Now, if you do the glide rescoring of just the top 2%, and in this experiment where we brute force screened 100 million compounds, that's 2 million compounds that had to be screened. We're able to recover 92% of the chemotypes that were found from the brute force docking from running the active learning approach and then taking the top 2 million compounds from that active learning approach and running glide explicitly on them to re-rank and then selecting the top 10,000 from the glide re-ranked compounds. Okay, and if we go a little bit further down the list to the top 5% of the active learning ranked compounds, we're able to recover 98% of the chemotypes. Okay, so what this says is that by screening, in this case, by explicitly glide docking 2,200,000 compounds, we're able to recover 92% of the chemotypes that would have been found had we brute force screened 100 million compounds. So that's over a 95% cost savings, and we're recovering the chemotypes with very good recovery of enrichment, with very good high enrichment. All right, now another question we could ask, because of the data from the Nature paper where they experimentally screened, we were able to ask, okay, well, how do we do in recovering experimentally confirmed hits with an active learning approach? And we're actually doing quite well with the active learning as well. We're recovering 85% of the experimentally known hits and 75% up to 100% if you go to 3% of the database screen. So the active learning based approach plus the glide rescoring of a certain tranche of the top scoring compounds from the ML method recovers a huge percentage of the experimental actives, again, while docking very small fractions of this library. And because we're only docking small fractions of the library, there are massive cost savings here. So glide itself, if we the brute force expansion took around 3,000 hours. If we run just a single ML model and use that versus an active learning approach, you can see massive cost savings in terms of the compute resources necessary to run these calculations. And that approach applies to other docking methods as well. Very similar results were seen by the Choquette lab, where it was a much faster method in this context from the way that they chose to run the experiment. And you're still seeing the massive cost savings. So this approach is general purpose. We've implemented it for our docking algorithm, glide, but I strongly recommend considering it for any docking algorithm that you're using. So take-home message is that machine learning enables us to sample these billion compound, purchasable compound libraries in order to recover hits in a way that is highly similar to the brute force docking, but at a fraction of the cost, the compute cost of brute force stocking. And we found that you're able to be able to recover the diversity of the hits that were found from brute force, as well as recover enrichment rates that are very high relative to the brute force stockings. And this continues to expand thanks to the Choi-Ket hypothesis, where as these libraries grow, we expect to continue to find even more potent and better scoring actives as these libraries continue to grow. And machine learning enables us to do that with significant cost savings. If you're interested in learning more, please check out our preprint, which can be found here. All right, so radically switching gears, going to talk about how we're using machine learning in order to improve hit suggestions coming out of these DNA encoded libraries. So DNA encoded libraries, these DEL screens, are a very powerful hit identification approach. It screens billions of compounds to find those with appreciable binding affinity to a given protein. And they don't require knowledge of the protein binding site's 3D structure, which can be an advantage in cases over structure-based virtual screening. Now, DEL screens, they're based on combinatorially generated ligand libraries that come from a split and pool process that from a small number of building blocks facilitates a stepwise ligand growth with DNA tags added per reaction, which enables the DNA to act as a barcode, indicating the building blocks and the reaction reagent cascade that created each of these ligands. Now, those billions of compounds are created. This library of billion compounds is created, and they're assayed against an immobilized protein. And ligands with appreciable activity to the target remain attached in a post-wash step. Now, vanishingly small amounts of the compounds that bind to the target remain after washing. So to determine their identities, the DNA on each of these compounds is separated, then amplified and sequenced. And based on that sequencing result, you're able to tie back to the DNA barcode and tell which reactions and building blocks were used to make the compounds that bound best, facilitating resynthesis and assay without the DNA linker. And this has become a very common approach. Number of success stories from DEL screens across a broad range of targets, including difficult targets like GPCRs. And the method is very powerful, but it does have limitations. There's a fairly high amount of noise in these experiments. And as the number of compounds in the library grows, as we go to the right-hand side of this plot, the signal-to-noise ratio decreases. Basically, you're looking here at a copy count, and you're looking at the copy count relative to the average. And so as the number of copy count average decreases, as you have greater numbers of compounds, it becomes harder to find signal. And the copy counts have to be significantly greater over the average in order to be able to really come out of these high throughput screens. So what we want to do is we want to enable larger screens with DEL libraries, but that means we need to find ways to be able to dig into essentially more of the noise, the average above the copy counts that are above average here, and be able to pull out compounds. Now, a second thing we wanted to accomplish is we want to find better compounds. A lot of the compounds coming out of these DEL screens are big, they have permeability challenges, they need significant development in order to get to a hit you want to carry forward with. But there are lots of compounds that have better properties within that space. We just need to be able to pull them out. So we need to amplify the signal to noise ratio. Now, how do we do this? Well, we're proposing using machine learning to increase the signal to noise ratio, which then will facilitate recovering false negative hits and increase the pool of candidates with better properties. And the basic idea is to train ML models against the DEL screen experimental hit rate data, which is normalized, and then develop a scoring function across the different experimental conditions typically used in DEL screens to help recover these false negatives. So we're basically using the ML methods to smooth the data and make it easier to pick out compounds that are above the average, but below the signal to noise ratio experimentally. And then we'll use these scoring functions to re-rank the DEL hits in order to be able to identify these better compounds. All right, so how are we doing this? We're training an ensemble of using AutoQSAR deep chem methods. There are typically multiple experimental conditions. We're creating, separating those out, creating models for each of those conditions. 15 models are created per condition, were created for this experiment with a collaborator against 50,000 hit ligands and 50,000 ligands that are accessible from the DEL library that aren't hits. in any of the washes, any of the conditions. Now, the example we're discussing today, there were 6 conditions and 2 control conditions. So there were a total of 18 conditions, 15 models each. So 120 models were created, took 3 days of compute resources on a single GPU that can be parallelized. And then for each of the 120 models, 11 million possible Dell library compounds. These are everything that had a readout from the Dell screen experimentally. They were evaluating, leading to a total of 1.3 billion ML predictions, which took 24 hours on a single GPU, which can also be run across multiple GPUs. So as you can see, the overall computation required here is not that significant. Now, one of the key decisions you have to make is what counts as an active. And so we looked at different, the ability to separate a high copy count from low copy count compounds from these ML models. Each of these is a different condition, ML model prediction coming from a different condition. And you can see that if we use the copy count greater than 2 for this particular example, we have good recovery of the compounds that show copy count greater than 2 and separating those from the compounds that didn't. And so this is exactly what you want to see, good performance. If we had perfect performance here, it would suggest that we're overfitting to the experimental data, which we know is a little bit noisy. Now, this slide here shows relationship. If you look at the experimental copy count data between the different conditions, 1, 2, and 3 are related, 4, 5, and 6 are related, 7 and 8 are controls. And if you compare the machine learning models, each of which is created to a separate condition, you can see that we're identifying the relationships in a pretty reasonable way here. The first 3 conditions are related. The 4, 5, and 6 are related. And so we were hoping to see relationships between these, and we actually do, which is fantastic. Now, the numbers here for the machine learning scores are higher on average than they are for the experimental copy count. And there's a baseline correlation basically in every cell where certain chemotypes can dominate, because certain chemotypes are going to hit every single one or large numbers of these different conditions. And so there's a baseline similarity that's to be expected here. But this is doing exactly what we wanted to see, where we're seeing relationships between the related conditions coming out of the ML model, which suggests that it's boosting the signal to noise ratio and it's amplifying that signal. All right, now we have these controls. One of the controls is that where there's no protein in the vial. So anything that sticks is going to be false positive, likely. And then another is where there's only cofactor. And so what we want to use is and you can see there's pretty good relationships between these controls, the negative controls, and then the positive experiments. And so what we're looking for are ligands that show a good score in the positive, so the positive screens, and low scores in the control screens. And so to do this, we put together 2 scoring functions based on the ML models that were created. So scoring function A, SFA, and scoring function B, SFB. Okay, and so of the conditions, condition 1 was flagged to recognize orthoallosteric binding when you have no cofactor, which is necessary for biological activity. Then you have 2 conditions for allosteric binding, and then a control where you have no protein. And this scoring function is weighted, so we wanted to boost allosteric binding, so the X here is 2, and we wanted to reduce the score based on if it gave signal when there was no protein to bind to, okay? So that's Y here is -5. And then we did the same thing or similar thing where you have a cofactor. So this is the more biologically relevant set of conditions. We wanted to capture orthoallosteric binders as well as allosteric binders with a bias toward allosteric binders. And then here, we're flagging against when you recognize binding when there's only a cofactor and no protein present. So we put together these 2 scoring functions based off of the ML models that were trained against the Dell experimental data. And one of the things that was found that was really interesting is each of these models had 1 negative control included. And what we found was the scoring function B was able to recognize and treat its high scoring compounds were devoid of the compounds that showed both positive high scores for both controls, for control 7 and control 8. So these are the high scoring compounds. And you can see they have low scores both for controls 7 and 8, even though only 7 is included in this score. While as if we looked at scoring function A, which had 8 included, you can see we have low scores for 8, but high scores for 7. And this is dominated by a single chemotype collection of sulfones. These are really artifacts from the experimental screening. And so we wanted to make sure we filtered these out. And scoring function B, not only is it more biologically relevant to the experiment our collaborator wanted to run, but we also, in the top scoring compounds, they were devoid of compounds that scored really well in both of the controls. So that's perfect. So we decided to move forward with scoring function B. And now what does the machine learning approach here, where we develop scoring function B based off of these individual ML models, give us? Well, if we compare the scoring function B by the experimental copy count, so we use the experimental copy counts instead of the ML predictions, and we compare that when we use the ML predictions, and you can see these are the likely false negatives that the ML method suggests we should examine to try and recover, because their copy counts are not very high. You can see there are compounds with much, much higher experimental copy counts. This is where there are compounds in good agreement with the ML and experiment, and these are compounds that the ML method is suggesting that are likely false positives because they're showing signal in the control. The only way to get a value of 0 in the scoring function B or lower is if you have significant signal in one of those two controls, and in fact, in one of the controls in this particular scoring function. All right, so the ML is telling us, have a look at these compounds to try and find greater diversity and better properties in the compounds that you want to experimentally test. And so the original hit list from Mushi is shown here. So, and these compounds, as you can see, have very large molecular weights, permeability, likely to have permeability problems for a number of these compounds. And so what we wanted to do was use these compounds, again, from the previous slide, and go through them and try to find compounds that had better properties that were likely still to be hits. And so we chose the top 100,000 ligands by the scoring function B score. We then re-ranked based on the experimental SFB score. We then re-ranked by the machine learning score. And then we used property filters looking for smaller, more reasonably sized ligands with permeability that's in a much better range. We applied diversity selection and then made the selections. And what's shown here, top 10 compounds, these are the top 9 from the DEL screen that were shown in the previous slide. These are the top 10 coming from the ML DEL suggestions. And you can see in much better property space with regards to molecular weight, with regards to the number of rotatable bonds, polar surface area, A log P, hydrogen bond donors, and acceptors. So this is perfect because these compounds are going to be far better as you move from hit identification into a hit to lead. And they still showed signal. In fact, the hit rates from our compounds and the hit that were suggested, the hit rates from the Wuxi compounds were very similar. Confirmed many actives with a hit rate of around 30%. And now this is great because what the experimental results are taking from are the compounds that showed the greatest signal to noise ratio. So the compounds with the highest scores here. Okay, and you can see these compounds, there are a number that are well above the noise. What we're able to do with this ML-based approach is smooth through the noise and be able to pick compounds from much more noisy region of the experimental space in order to pick compounds that have much better properties. And those were confirmed experimentally. All right, so as a side benefit, we also found a number of confirmed truncates where the reaction cascade doesn't actually lead to the full molecule. These compounds tend to be really positive because they're, again, smaller with much better physical chemical properties. All right, so in conclusion, machine learning methods were very valuable both when both experimental in this experimental DEL screen as well as in virtual screens for being able to help recover high quality hits in terms of properties while minimizing costs. So with virtual screening, we're internally switching over. We're almost exclusively running these active learning screens against these billion compound libraries in order to minimize the cost relative to brute force while still benefiting from the shortcut hypothesis and recovering a majority of the hits that have very good chemistry and more potent compounds coming out of your screens. And then with the DEL libraries, we're helping to boost, machine learning is helping to boost the signal to noise ratio and help find compounds with better physiochemical properties from the experimental data where it's showing signal, but it's not strong signal, and still have hit rates that are on par with those coming from just choosing from the highest hit rate or highest copy count compounds. Now, thanks very much for your attention today. If you're interested in learning more, I strongly recommend contacting sales@schrodinger.com for Active Learning Glide or the ML enabled Wuxi Dell Light screen. And if you're interested in learning more about virtual screening in general, from small libraries to billion compound libraries, consider looking into our new online course, High Throughput Virtual Screening for Hit Finding and Evaluation, which can be found on our website. So thank you very much. There are a number of other people I'd like to thank here, particularly Stephen Jerome, who ran the Active Learning Glide experiments, working closely with Carl Leswig. And on the Dell Light side, Vicky Fair, Jeremy Vendome, and Cesar de Oliveira. Man, I butchered that, apologies. All run under the management of Robert Abel. So thank you very much for your attention, and I look forward to answering as many questions here as I can.
Thank you very much, Matt, and thank you for a very concise but information-dense presentation there. For anybody who watching back at home, if there was anything that you wanted to go through again, don't worry, we'll send you a link to the entire recorded presentation so you can watch the whole thing. Any bits you just wanted to go through once more, that'll be in your inbox shortly. Now, we've had got a couple of questions in. I've got a question that we talk about things like machine learning, big data, and all of these sorts of things, and they stem from the language of maths and statistics and programming. They don't stem from the language of chemistry. We're Chemistry World. Our audience, yourself, are chemists. Do you need to have an expert knowledge in programming or statistics in order to take advantage of these sorts of approaches?
So absolutely not. With the active learning approach, we have an interface. You can open up 3D modeling software, Maestro in this case, select your protein ligand complex that you want to start with. You have to have a known protein binding site in order to run an active learning or any kind of virtual screen for that matter that's structurally enabled. And you literally pick the ligand in the binding site. You select the library that you want to use. You can apply more sophisticated things like constraints if you'd like to. And then you can hit a go button, and it's really that easy. Now there is support to set up the calculation machinery. You typically want to run these on a cluster, ideally a cluster that contains both GPUs and CPU nodes. But if you don't have those types of resources, at least here at Schrodinger, we have a virtual cluster that we can basically spin up for you and then provide it to you, and then the calculations can be run on the cloud without any IT setup on your side. And we also have a service where we'll run these for you if you don't want to touch it at all. So a range for people depending on their technical capabilities, but no, there's no programming here at all. And you can run it from the command line with just one single command.
Excellent, that sounds good. I confess my statistical and programming abilities are perhaps not what they should be, and it's a common question actually in these sorts of webinars where people say, do I need to go back to school and learn how to program in order to be part of the future of chemistry? And it's good to see that companies like Schrodinger are taking that step out and making sure that you can take advantage of all of the new developments without needing to go all the way back to the beginning and learn how to program from scratch. Right, a couple of good questions just come in. Let's go for this one from Anthony, who said, how well do docking-based approaches work for proteins with flexible binding sites?
So it's going to depend greatly on the level of flexibility and the induced fit nature of the binding site. So for targets like GPCRs, where there is a high flexibility, a number of virtual screens have demonstrated success in the literature, and we've seen it internally in our drug discovery applications group as well. But it's going to be very dependent on selecting the 3D structure of the binding site that best reflects the actual physics and biology of the chemotypes that you're interested in. And so what we've found over the years is for targets with a lot of plasticity in the binding site, you're going to want to use an induced fit docking kind of approach if you can, in order to really examine and set the 3D structure ideally for particular chemotypes. Some examples, for instance, you have tyrosine flips that can be common, and they can block off entire sections of a binding site, making it so only smaller ligands or only larger ligands will fit and bind successfully in particular conformations. And so depending on the target chemistry of your project, you may want to focus on one or the other of those structures. So then selection of the initial structure you want to use can really play a huge role. The protein structure you want to use in the docking play a huge role in the success of the virtual screening experiment. And one of the things we've seen a lot of success with is using ensemble-based approaches. So instead of running just one docking experiment to a single conformation, you can run docking experiments into a number of these structures, which can come from, say, for instance, these induced fit docking approaches with, if you have known material to work with based on the chemotypes that are already known.
Thank you very much for that great question. We're running low on time. We should put a couple more in. So Shruti has said, how do you think pharmacophore mapping and active learning compare?
Sure. So pharmacophore mapping is a very powerful approach, and it's a nice fuzzy approach in that it allows intrinsically for flexibility to deal with some of the plasticity that was talked about in the previous question. Active learning based approaches standalone are 2D topological methods. So they're using featurization you can think of as fingerprint like. Okay, so they're really more ligand focused in terms of the 2D topology than a pharmacophore based approach, which is really looking at having certain chemistry that's considered as equivalent. So what we've done is you can actually apply shape-based constraints in docking and active learning docking so that you can apply the concepts of a pharmacophore screen where you say, I need to find chemistry that is going to satisfy hydrogen bond donor or acceptor or is going to be hydrophobic in this particular volume. And you can apply that in these docking experiments on top of the docking itself. And this is commonly done as a way to bias the experiment into particular regions of ligand chemical space that you want to see examined. So I'd say that they're complementary. We also will often run shape screening experiments, which is, they're different than pharmacophore in that you don't necessarily have directionality, but they're similar in concept where you're looking to find what chemists would recognize as these features in particular regions of 3D space relative to one another.
Excellent, thank you. And again, another great question. So this one is from Marino. Do you see differences in the result scoring when you run the machine learning on small or bigger compound collections? Is there a bias based on your initial library?
Yes, there is absolutely a bias based on the library. And it really boils down to, well, we haven't proven this conclusively. We talk about this a little bit in the preprint that I noted earlier. But we examined explicitly Sigma library with 8 million compounds, and we screened that both brute force and with active learning. And what we found were the hit rates, the ability to recover the top scoring compounds from the brute force screen in the active learning process were about half that we observed with the zinc work, for instance. And the working hypothesis there is that these on-demand combinatorially synthesized libraries have a particular construction that leads to a lot of chemotypes, but then a lot of decoration around each of the chemotypes. So unlike a Sigma library where these are off the shelf, and so they're not having as many decorations per chemotype. And you just have far more shots on goal when you've got a lot more decorations per chemotype. Let's say, for instance, you have a methyl group that sticks into the protein and it kills that particular structure. Well, maybe that was a very, it could be a successful chemotype if it weren't for that single methyl group, but you only have one example of that in the Sigma library. Because the enamine real library is like 100 times larger, something like that, you typically, when you have these chemotypes, you'll have 100 decorations around it. 150 decorations, more sometimes. And because of that, you just have far more shots on goal to find these chemotypes. So We strongly recommend using the active learning approach on billion compound libraries. We actually don't recommend using an active learning approach on these smaller libraries, and instead we just recommend brute forcing the more traditional sigma, Molport style, 10 million compound libraries.
Excellent. Let's squeeze in one last question. I think this one's from Jeffrey. It says, what is the typical time to loop through virtual screening and the DNA encoded library execution and hit confirmation and the medchem follow-up?
All right, so if we want to run the virtual screen of these billion compound libraries, we'll turn them around in a week. It's going to depend on the number of docking calculations you're able or willing to run simultaneously. We'll tend to run these on hundreds of processors simultaneously. Now, it can take longer if you have fewer numbers of CPUs available for the docking, for instance. The Dell screens, experimentally, you send it off to Wuxi, they'll send back the results. And then in order to run the ML-enabled Dell screens, we partner with Wuxi, particularly with their Dell Lite product. And so we're able to gain access to the raw screening data, which is necessary for the ML. We'll typically turn that around in a week or so as well. Although, as you could see, as I showed earlier, the computation time necessary to generate the models is really measured on the order of a day, maybe a couple days if you only have 1 or 2 GPUs. So most of the time there is actually in the analysis. That is more of a bespoke, create a custom scoring function based on the biology of the screen. And then based on that, you can make selections and reselect essentially from the hit compounds that shows signal in the original Dell experimental screen. So for active learning, virtual screening, a week turnaround for us is going to depend on the number of licenses that you have. We have a nice calculator on our website actually that you can use to estimate that time. And for the Dell screens, it's not really what I would call time limited. It's really on the computation side, it's really experimental because once you get the hit list back, you have to synthesize those compounds from scratch, or they're typically not purchasable. And then once they're synthesized, you need to feed them through the assay. So that's really the limiting factor there, not the calculation.
Excellent. Thank you for your question, Jeffrey, as well. We have run over slightly. Thank you for sticking with us. But that is all we have for this Chemistry World webinar. I'm delighted to have you with us, Matt. That's Matt Rupasky, Senior Vice President of Life Sciences Products at Schrödinger and leader of Schrödinger's scientific and technical support groups. It's been a fantastic presentation, a lot to take away and think about. I hope that the audience, especially the 27% of the audience who find that machine learning has common and significant impact on their research, will really have taken something away from this, and hopefully we'll be in touch and we'll follow up with some of the links that we've shared throughout the course of the webinar. So thank you, Matt, for joining us, and thank you, the audience today, for joining us for the live event. One final reminder, you'll get a link to the recorded version of this webinar so you can watch it again at any time if there's anything you missed or just wanted to go through again. And we'll also include a link to a certificate in there. That's our way of saying thank you to you for attending live. Also, a huge thank you to Schrödinger. They've been a partner with us for several webinars and will continue to be throughout 2021. So have a look at chemistryworld.com/webinars and you'll see upcoming events with Schrödinger where you can learn more about similar topics, often looking at different areas of chemistry and how these sorts of computational approaches can make chemistry in the broader view that bit easier, that bit more efficient, to make you find things you just wouldn't have done otherwise. We've just put a link in there for the next Schrödinger webinar coming up. That is once again available for free. You can register now. If it piques your interest, then do please register, and we'll see you for that webinar in about a month's time. So huge thanks to Schrödinger, they're an excellent partner for Chemistry World, and we're really delighted that they continue to bring us brilliant people like Matt Rupasky every month. So that's it for this Chemistry World webinar. Thank you one final time for getting involved, for asking all your questions, and for attending live. Thank you to everyone who asked a question that we didn't get around to answering. We have taken a record of them. We will send those questions to Schrödinger. If they are able to help you out and get a specific answer to you, then I'm sure they will. So that's it. Thank you for joining us. I'm Ben Valsler, Chemistry World's digital editor, and I will see you for the next Chemistry World webinar. Thanks again.